All right, we're going to turn it over to you.
Wonderful.
And, take it away.
All right. Well, welcome. We are from the New Mexico School for the Arts. We are team number 59. My name is Rowan Janssens.
I'm Madeline Kingston.
And I'm Brandon Morrison, and this is It's About to Get Lit Up in Here. Modeling forest fire risk in northern New Mexico. So for our project, we wanted to model the spread of forest fires in the Santa Fe area in New Mexico. We are doing this because we found that evacuation notices during forest fires are oftentimes insufficient and put civilians in danger because they are unable to predict the fire's movement in time to bring the people to safety. In order to do this, we wanted to implement different variables, including slope, wind, and fuel type, to more accurately model the behavior of a fire. We also wanted to pioneer a new way to tune models using empirical data and by using physical experiments to gather data that will increase the comprehensiveness of the model. So why are forest fires so important in New Mexico? Well, New Mexico has had a long history of fires, some recent ones including the Los Conchas fire in 2011, which burned over 150,000 acres of land in a little over a month, and the Whitewater Baldy Complex fire in 2012, which burned over 300,000 acres of land in about 6 weeks. Scientists in the past have attempted to model forest fires, like Richard C. Rothermel, who, in his study, A Mathematical Model for Predicting Fire Spread in Wildland Fields, he looked at different variables and how they affected the spread of fires. One of these variables was slope, as you can see on the right. He was able to create a graph of the effect of an upward slope on the speed of a fire, where he showed that fire does increase speed when going uphill. It can be seen that his model isn't perfectly accurate. He did his study in 1972, so that's an almost 50-year advancement in technology, which has allowed for better accuracy, like having the ability to tune according to actual fires. Also, he failed to mention the effect of a downward slope and only investigated positive angles and their effect on fire spread, which is something we wanted to look more into with our project. So, when approaching this project, we focused on 3 variables that change the way that a fire spreads. Our first variable that we focused on was slope. This is the variable that we spent the most time on. We've spent about the first half of this project on slope, just that. Through our research, we saw that fires spread faster going uphill due to the convective heat that pushes the heat of a fire upward, burning objects above it faster than below it. Next, we focused on wind, which is also important when looking at forest fires because it's able to dramatically increase the speed of a fire and also change the fire's direction in a moment's notice. Lastly, we looked at fuel type. Fuel type is able to affect a fire spread in multiple different ways. First being that the different types of fuels are affected by fire in different ways. Some fuels burn faster than others. Also, the density of a forest affects a fire spread because a more dense forest will burn faster and more than a less dense forest. So all 3 of these variables were important to consider when approaching a model.
So as Brandon explained, our first variable that we chose to examine was the effect of slope on fire spread. And to do this, we designed a physical experiment to gather empirical data on which we could tune our model. And in the physical experiment, a sheet of A4 graphing paper is suspended in this tray with spikes, and we isolate a perfect 216 millimeter square right here that we look at for the burn. And the whole tray is set on 4 ring stands so we can adjust the angle of the entire page, and we refer to this as the incline angle in the future. Then we take several time measurements as we burn the paper, namely the uphill downhill or up down time relates to the uphill downhill direction right here. We also take the across time, which refers to the across direction right here, and we also take the total time when the entire paper has burned. And we light the paper in the lower right-hand corner for uphill burns and the upper left for downhill burns. And here we have some raw data from the physical model, and this is the up-down time, as I just explained. And this data is given in seconds. So we took between 3 to 5 trials for each incline angle between -60 and +60 degrees. We also took an additional trial at -10 and +10 because we believed that at these 2 points we would see the most change. So we decided to take more trials towards 0, if that makes sense. But of course, a time measurement in seconds is not incredibly useful in implementation into a computer model. So the first step in creating our computer model is we need to scale this data. So we take the average of all these points so that we've got a single data point for each of the angles, and then we divide that time in seconds by the length of the paper, which happens to be 216 millimeters, and then we multiply by 100 to change it from seconds to centiseconds. And as you'll see in a moment, here are the scaled points. And these black dots are the physical model scaled points represented in ignition delay time in centiseconds per millimeter. And I know that unit probably sounds somewhat unfamiliar, but I'll do my best to explain it. The ignition delay time will be used in the computer model to calculate how fast the computer model will walk around, per se, if that is how we compare the fire. So for a negative incline angle of, let us say, 60 degrees, we have a much longer ignition delay time, which means the computer will have to wait longer before it burns or spreads the fire to different points. So having to wait longer will result in an overall slower burn rate, and that will correlate to an overall longer burn time. In contrast, if we have a positive incline angle where a very short ignition delay time is calculated, that means that the fire will spread much quicker because the computer won't have to wait as long to spread that fire, and then that will result in a faster burn rate and an overall shorter burn time. So this curve right here is then fitted using Igor Pro, which uses the least squares method, and we fit a sigmoid function displayed by this equation up here, and it's also plotted with this blue line right here. And this equation it includes the standard deviation of all these points, so it's a good match of this data, and the sigmoidal function is going to be useful throughout the model to calculate the ignition delay time, which will be then used to determine the effective slope on the model. We are not exactly sure why it's a sigmoidal curve, but sigmoidals seem to fit the data best, and it's going to be useful in the model. And so to implement it into the model, we have to do several things. First of all, let me tell you, we are using NetLogo, and the basic computer model is the first revision of our model. It's 1.0 per se, and it mimics the physical model exactly. And by that I mean its size is exactly the same. The computer model, the basic computer model, is 216 patches squared, and as I said, the physical model is 216 millimeters squared. So they're the same size. Furthermore, 1 centisecond in the physical model is equivalent to 1 tick in the computer model. So by that sense, they are identical. And in the basic computer model, all incline angles are equal across the plane, if that makes sense, because as we saw in the paper model, it's just a flat plane. But regardless, we still would like to show you how we calculate the incline angle between any two patches, because in the future, we will have a variable terrain, and this will be applied there. So to calculate the incline angle, we take the inverse tangent of the distance, the change in elevation between any two patches, and then the distance between those patches. So since the fire can spread to its 8 neighbors, we've got 2 different distances, right? For the intercardinal directions, we've got square root of 2 millimeters, and for the cardinal directions, it's just 1 millimeter. And then the change in elevation is just the differences between the elevations assigned to every patch. So then we take that incline angle that we've calculated through this function, we plug it right in to our theta, per se, in this equation that we derived in the physical experiment, and that's going to spit out our ignition delay time. And that's how long the computer will wait before it spreads the fire. So let's say this patch is on fire, and then it calculates it's going to have to wait 10 centiseconds before it burns this patch. It will then wait 10 centiseconds, and then this patch will turn red and be ignited. So this is what the basic computer model looks like. As you can see, we've got a perfect square. We've got kind of a color gradient indicating this is the top of the hill, this is the bottom of the hill, and this is the top, and this is the bottom, vice versa. As you can see, on an uphill burn, such as this positive 41, it burns much differently, and there's an observable different propagation of the fire. And for -40, you will see a different again. But more interestingly, we have a video prepared that compares the two side by side in real time. So this is -40 degrees in both. And then we've got the computer model on the left and the physical model on the right. Again, this is the across direction and the across time. This is the up-down direction correlating to the up-down time. And this can be seen as the top of the hill, and this can be seen as the bottom of the hill. In a moment, we're going to zoom into the physical model, and we're going to get an overlay of kind of the logic that the computer model is mimicking when it is calculating its spread. So in this case, the red squares represent patches that are on fire, the green squares represent ones that the fire can then spread into, and the black squares represent fires that have already burned. Sorry, let me finish this video. So we're going to get the across times popping up here. You can see that they're very close with one another. We got the across time from the physical, from the physical and from the computer. And then we're going to get the down times popping up, and these are even closer to one another. And we're finally going to get the total times of the two models compared side by side. As you can see, the physical model burns totally a little bit slower than the a little faster than the computer model. But here we compare the computer model and the physical model and their up-down times in seconds with one another. So the computer model is represented by the blue line. The physical model, again, is those black dots. And this is the up-down time in seconds along the various incline angles. And what you'll see is that the computer model and the physical model are very close to one another. So in that sense, on the up-down time, the computer model is very predictive of the real world and therefore pretty accurate in our opinion. However, for the total time, we see a larger deviation in the negative incline angles, but for the positive incline angles, it's still pretty close with our observed physical data. So that concludes the basic computer model and our analysis of slope. And the next variable we're going to be discussing is wind. And at first, we decided to take the same approach and develop a physical experiment to gather empirical data on which we could tune our model. However, the physical experiment was just restricted due to our setup, and so we decided to skip the physical component and jump straight to a mathematical approach and implementation. So in this implementation, we have the ignition delay time, which we already calculated using that equation that I showed on a few slides ago. And then we're going to take the component vector of any wind in a given direction that we're calculating spread for, and then we're going to manipulate that ignition delay time, either making it longer or making it shorter depending on how the wind is blowing. So if we were to do a physical experiment to gather some data, we could remove one of these variables, particularly this beta correlating to wind strength. We could have another function that shows wind strength and how it affects fire. So that's one way we could tune our model with physical data, and we hope to do something like that in the future. Here's a little picture of what happens when we do wind in our model. Here we have a southern wind, which means it's blowing north, and we can also see a clear northern propagation. All of these fires started in the center of the plane. And as you can see, the fire also spreads very visually in the direction that the wind is also blowing. So that concludes our analysis of wind.
So the final variable that we looked into was fuel. So we used the most commonly used model of fuel types, which is the Anderson fuel type model. This distinguishes all flammable vegetation into 4 different groups of grasses, brush, timber, and slash. This model was designed to be used with Rothermill's spread model, which means that it's useful with our model. While different fuel types may have different burn rates, there is not a lot of data for those particular burn rates. And our model could eventually identify those rates by using the same variable tuning method that we used for slope. So we would collect burn rate data from wildfires on camera or from a physical experiment, account for the variables of wind and slope, which might change the way that the fire spreads, and then based on that, understand how the fuel type that is present burns and what its burn rate is. So after having completed the basic computer model and gathered data for all 3 variables, we were able to culminate this information in the GIS computer model. We got the GIS data from landfire.gov and converted it to a NetLogo compatible form using QGIS. This image of the model shows a NetLogo plane that has assigned each patch to have an elevation corresponding to a location in the northeastern Santa Fe area. With this data, each patch has the potential to represent as small of an area as 10 meters squared, but for our purposes, each patch is now equivalent to 82.5 meters squared. And as you can see, there are a few locations labeled in this map to orient where this elevation applies to. So then we overlaid on top of that the fuel type coverage for the area. So water, urban, and bare fuel types are shown and do not burn. The tree category accounts for fuel types 4 through 10, which are the shrub and timber groups out of Anderson's 13 vegetation fuel types, and treats them all to burn at the same rate. Again, this shows some of the defining features of the area, including the Santa Fe water reservoirs and the highway and downtown area. So this is an example of the model burning with Santa Fe's elevation and random tree placement. So this is not including the fuel types shown in the last slide. The basic computer model's definition of slope effect still applies, even on the non-uniform slope version with the GIS elevation. So when a fire starts on top of a mountain, there is therefore a downhill spread, and it is a smaller and slower burn. Whereas when the fire starts in a valley, it's an uphill spread and will be larger and spread faster. So these complete models allow us to explore phase transitions in the basic and GIS computer models, as well as create a fire risk map for the Santa Fe area. And we think that these are the best ways to demonstrate the competence and significance of our models. So in all fire models, there's a critical density where fires will go from burning very, very small percentages of the forest to almost the entire forest. And locations where the forest density is at that critical percentage are at high risk and have high unpredictability, which means that potential firefighter and emergency effort placement is more important in those areas because of more potential to stop the fire. This graph shows a sweep of forest densities on a flat plane, so the basic computer model, with the and then calculating the average percent burned. In this case, the critical density or phase transition is at around 40%. So we repeated this parameter sweep for all angles by 5 degrees to measure whether or not it affected the critical density. So what we found is there are 3 distinct phase transition groups for the basic computer model. From 0 to 20 degrees incline, the critical density is around 40%, and the phase transition is very steep, whereas with angles 25 to 55 degrees, the critical density is at around 50% and slightly less steep. And the particularly different group is from 60 to 90 degrees, where there is a slight phase transition at around 50% density, and then at 90% density, it finally spikes up to burning 100% of the forest. This graph only shows positive angles, but the negative angles correspond to this data because we started the fire in the middle of our model for this particular parameter sweep. So then we were able to explore how fire spread with randomly placed trees on the GIS model. So this is a parameter sweep of density with the Santa Fe elevation. As you can tell, there are 3 different regimes. 0 to 60% cover has very, very little burning, whereas 60 to 80, the percent burn becomes more sporadic and increases. And 80 to 100% cover, there's that phase transition spike with a critical density of about 80, where suddenly almost the entire forest is burning. So this is just an animated image of what the runs from that parameter sweep look like. And you can clearly tell when it spikes to almost 100%. So this next slide shows the frames broken down, and the 3 regimes of percent burned are clearly visible. The 3rd row shows the second regime where fires are significant but not catastrophic. And the bottom row is the third regime, which is after the phase transition, and almost 100% of the forest burns. You can see that the critical density is at about 82%, as shown in the previous graph. So accounting for fuel types 4 through 10 out of the 13, we calculated Santa Fe's actual forest density to be around 68%, which means that, as it is labeled on this graph, which means that fires will likely be under 10% of the forest, but are mildly unpredictable. Finally, we were able to create a fire risk map for the Santa Fe area. This is created from a parameter sweep where a fire is started at every ignitable location, and then the percent burned for that location is measured. So it shows that the area that will burn if a fire originates in a certain spot. So this is shown in the image by locations that burn more of the forest, or have a higher percent burned, are lighter in color, whereas areas that, if ignited, will burn a smaller percent of the forest are darker in color. So it basically shows the risk for potential forest fires in certain areas. This is a useful tool for anyone who interacts with the forest in any way, or does what they can to prevent forest fires from affecting people. And also, our eventual goal is to measure these kinds of fires in real time to make real-time predictions about high-risk areas for a forest fire that is in progress. So our technique of using the physical data and tuning the variables in our model that affect the rate of spread could aid in calculating this real-time burn rate for wildfires, rather than a prediction of what would happen if a fire started. Instead, we would be able to predict where a fire will end up based on the location that it started and the variables that we have identified previously.
As Madeline has reiterated, this is an example of how one could use live video to calculate rate. So these guys at SimTable have created this video where they are taking a video and mapping on some lines in which they can calculate the burn rate as it relates to various fuel types on this mountain right here. And as you'll see in a minute, they're going to pop up the elevation, the fuel type charts that they've calculated. So these have a little histogram of the fuel types. So we hope to do something similar like this in the future, where we're using video to calculate rate as it relates to both fuel and wind and even slope in the real world.
So there were some limitations that we faced when working on this project. First, a piece of paper is in a forest. There are differences in variables that affect how a fire spreads and how fast it moves. But a paper was good for getting a base model down when we were first starting out, and it helped us to develop the equation that we would use to implement into the model. Another limitation we encountered was that in our computational model, we only got the fire to spread in 8 directions, when in reality, a fire can spread in an infinite number of directions. And that changes its behavior when compared to how it looks in the model. One way of fixing this would be to add a heading over the fire in the model so that it could represent that having an infinite number of directions and be more accurate to actual fires. We also failed to implement the different burn rates for the different types of fuels that are seen in real life, but we do hope to do that in the future. And we also plan to do more physical experiments and get the data on real forests in the future. And we hope to make our model more easy to apply to other locations, for example, California or Australia, in order to make our model more accessible to the whole world. Finally, like Maddie and Rowan said earlier, we hope to use live video to calculate the rate and predict fire in real-time models, so we can more easily have real-time predictions of forest fires.
That's right, and these are our references. Does anyone have any burning questions now?
Nice job, guys. Judges, we have time for a couple questions.
Let me ask a question. So you have an impressive array of analysis, but you began with a physical experiment. And I know you said it's just a sheet of paper, it's not the forest, but you had a proper setup with a fume hood you could easily use some other materials to see how different materials burn, right? You could use wooden plank and so on, right? Did you try something like that? And why did you settle on a sheet of paper?
Unfortunately, we did not. Yeah, we were kind of limited on both time and materials, so we were unable to expand our materials. But in the beginning, one thought we had that we could model fuel type with our current setup would be to like perhaps print things on the paper. We were thinking that maybe like printing like a pattern with ink would somehow maybe manipulate the way it burns. So we definitely thought a lot about how to, you know, bring all of these variables into the lab, but unfortunately, the limitations just made it practical to do slope.
Thank you.
Yeah, so this is Dave Janke. Nice job on integrating the physical model and then going on to a variety of details in your computer model. A suggestion for your physical model would be to sort of dampen the paper in various ways so that you could change how it burns and you know, that's a real problem out in the woods. You can get a rainstorm to come across in a certain area, and that will change fire dynamics a lot. Another thing that I'd be interested in you thinking about and responding to here is how does overlapping fires sort of impact how your model might work and how you might integrate that? Thanks.
I mean, I have an answer. Do you guys have anything to say?
Well, I think I can say something about speaking of moisture. One of the things that we would like to implement in the future in terms of fuel type is including how saturated the forest is with water. So in our situation, it makes a difference that the area is so dry. So hopefully in the future, we will able to group that into kind of a fuel type thing. Again, as Rowan said, we had originally thought that we might try printing ink patterns to represent moisture. However, it wasn't plausible to do while we were focusing on slope.
Yeah, I think the reason why, because we were thinking about doing something like that, maybe dampening the paper or printing ink, but we wanted to really focus more on slope when starting out our project. So it was simpler to just refrain from doing those and instead to focus on the slope and get our data from that.
And as to your question, I think that in the future, like one thing that I think we observed is that like the size of the flames is often very important in determining like the rate of spread. So you could almost redo the model just based on the size of flames. And so like, yeah, when two fires intersect, you're gonna have much bigger flames overall. And so you could then use that to manipulate the rate of spread, because as you might have seen in the video, like right at the end of the physical model, we get a big kind of flare up and then it burns very quickly. But then like, so I feel like you could almost use that to like your advantage and instead calculate based on flame size.
Yeah, very good. And nice distribution among your team there, even in answering the question. Thanks.
So want to have any more questions?
Yeah,